Hello everyone and thank you for being here. Today I'm presenting our paper on probabilistic sparse subspace clustering using delay association. In recent years, in a wide range of applications of machine learning and computer vision, data has grown exponentially in terms of volume and dimension. Example of application for this problem includes face and image segmentation, when data includes image in high dimensional space and the task is to segment images into different categories. Video motion segmentation and action recognition, where the input data is a set of feature trajectories across a video and the aim is to record the different rigid bodies. Similar to many other applications, all these examples deal with data presented in high-dimensional space that naturally form clusters of low-dimensional subspaces. Recovering the low-dimensional presentation of data is an important step in understanding the data, estimating the structure, and recording the computational and space complexity of algorithms. Early methods such as principal component analysis try to find a low-dimensional representation of data when it runs from a single high-dimensional space. But in a large variety of applications, data is driven from a mixture of multiple subspaces in high-dimensional ambient space. In this case, we are interested in finding the best fit for each subspace. Since data points are unlabeled, we do not know in advance to which subspace they belong to. Subspace clustering is defined as simultaneously cluster data into multiple subspaces and find a low-dimensional subspace approximating all the points in a cluster. Formally, subspace clustering is defined as the clustering a set of data point x when x is a collection of n data points with an ambient dimension n from a union of c independent linear subspaces. The idea is that when a subset of high-dimensional data belong to one cluster, then all those points lie near a low-dimensional subspace. Therefore, each subspace can be represented by a small set of learned bases. Subspace clustering presents a distinct challenge in clustering algorithm which has a major difference with classical clustering methods like k-means. Classical clustering methods use a simple distance-based similarity between data points, but subspace clustering measures the accuracy of representing data point using a basis of each subspace. For instance, in this example, if these 3 points represent the basis for this subspace, then a point on the other side of the plane can still be represented using these bases in this subspace, even though it has a smaller distance to the points of the other subspace. Different solutions are represented in the literature to find subspaces. Spectral subspace clustering is one group of methods that use a two-step approach, building a similarity matrix and applying clusters using a spectral clustering. One way to build a similarity matrix is to use a geometric property of data, which is any point in the subspace can be represented as a linear combination of other points in that subspace. Both the sparse similarity matrix and the clustering results depend on each other. Proposed methods in the literature use iterative approaches to update the similarity matrix using the clustering results and subsequently find the clusters using the new version of similarity matrix. Clustering matrix Q can be hard clustering with binary value of 0 or 1, or soft clustering including continuous real values. Hard clustering can remove some important information where correcting misclassification can be more difficult. Soft clustering has the advantage of including continuous real values for reweighting the representation matrix in the next iteration. However, soft clustering has the disadvantage of removing less noises from the similarity matrix compared to hard clustering. In this paper, we propose an alternating method of subspace clustering. We estimate the reliability of cluster assignment for each point xi. If the reliability is low, we call the point uncertain and we delay its association to any cluster. Remaining points at this iteration are considered certain and clustered right away. This helps to improve the accuracy of updating the elements of the similarity matrix in the next iteration. The process starts by assuming that the initial cluster of subspaces are given. We group data points into two groups of certain and uncertain, in which we use hard and soft clustering assignment for these groups respectively. After that, we find assignment of the points to C clusters by a soft clustering matrix phi, which is an n by C matrix, and each element of phi ik represents the probability of point I belong to subspace K. In particular, phi ik is equal to 1 when point I is confidently assigned to cluster K, and phi ik is equal to 0 when point I is confidently excluded from cluster K. We can define the association matrix A as phi phi transpose. A is an n by n matrix, and element of Aij indicates the strength of connection between point I and point J in the dataset. Given A, we find coefficient matrix and similarity matrix, which indicate the connection between each point and all the other points in the dataset. So these two matrices A and Z are related to each other and represent similar information about points in the dataset. The association matrix A can be used to denoise the coefficient matrix D and get a better representation of data in their own subspace, while taking into account that coefficient matrix D can be lead to a more accurate recovery of association matrix A. We formulate the connection between A and Z as in this formula, where 1 is an n by n matrix with all unit elements, and lambda 0 and lambda 1 are positive trade-off parameters. The constraint Zii equal to 0 forces the main diagonal to be close to 0 to avoid degenerated solutions. Our proposed method jointly search for a sparse self-representation matrix D and the soft subspace segmentation phi that satisfies rank of phi equal to C. We alternate between finding the association matrix A and coefficient matrix D that we explain next. Given the similarity matrix, our objective is to find the association matrix A. Since the optimization framework is not convex with respect to A, we find the initial cluster for points by applying a spectral clustering algorithm that divides points into C separate subspaces using the similarity matrix. Given the hard clusters obtained from the spectral clustering algorithm, we need to determine the likelihood of a point xi belong to each C subspaces as the degree of association of each point with each subspace. Psi zi is found by keeping all the elements of the vector zi that are associated with subspaces K and setting the remaining elements to 0. Using this formula, we build the association probability matrix P, which is a n by C matrix with element of Pik being the probability of assigning point xi to subspaces K. The delay association parameter is calculated by finding the average affinity between points of a subspace. To find that, we first define the affinity matrix M, which is a C by C matrix and demonstrates the affinity between points in subspaces. The main diagonal of this matrix shows the correlation between points of a subspace and off-diagonal entries showing the similarity of points in different subspaces. We use matrix M to find the delay association parameter omega in each iteration. Using the delay association parameter omega, we divide points into two groups of certain and uncertain and build a soft segmentation matrix phi. Given an assignment matrix phi, we form association matrix A as an n by n symmetric matrix. By having A, we can find the coefficient matrix Z using this formula here, and then we alternate between finding A having Z and finding Z having A. An example of updates in association matrix A and similarity matrix Z over two sequential steps is illustrated in this figure. The data includes 3 subspaces and 70% intersection. As we can see, became more sparse and close to the block diagonal in the second iteration. Matrix A also could derive a better representation of clusters. Here, we compare the proposed method to the state of the art. In the proposed method, in each iteration, certain points give a better representation of points in their assigned cluster. Uncertain points have a chance of estimating a better representation before being assigned to any cluster. This has the advantage of converging to a more accurate solution when the subspaces have overlaps or when data is contaminated with noise or outlier. To compare the proposed method with the state-of-the-art methods, we use a syntactic data with intersection between subspaces. Each subspace has a true dimension of 10 with an ambient dimension of 200 and 100 points in each subspace. These graphs show the results for when the subspaces have 60% intersection and when we have 2, 3, and 4 classes in the data. This graph shows the decrease of misclassification as iteration continues. As it's shown, the proposed method reduces the misclassification error significantly. The complete summary of average misclassification error over 20 independent trials is shown in this table here for the synthetic data that we just explained. The first application we use here is phase clustering. It is shown that images of an object under varying illumination lies in a low-dimensional linear subspace of up to 9 dimensions. We use phase images from Yale dataset here to show the result of subspace clustering. Updates in association matrix A and similarity matrix Z over 3 consecutive iterations is shown here. Data includes 5 subjects. The misclassification error is changed from 7.19% to 1% respectively. The complete summary of average misclassification error of proposed method is compared here with the state of the arts. The first 4 rows of the table are 2-step graph-based subspace clustering methods. The next 6 rows shows the result of joint optimization methods in the iterative manner where both clustering results and subspace representation are updated. Row 5 to 7 are hard clustering based methods and row 8 to 10 are soft clustering based methods. The results are shown for 2 to 10 subjects. As we can see, the proposed method that combines both hard and soft clustering outperforms all the state of the arts. The second application is motion segmentation. It is shown that trajectories of a single motion lies in a low-dimensional linear subspace of up to 4 dimensions. The complete summary of average misclassification error for motion segmentation is shown for the proposed method and the state of the arts. The results are shown for 2 motions, 3 motions, and all the motions in Hopkins dataset. The proposed method outperforms all the state of the arts as is shown here. In summary, the main 2 advantages of the proposed methods are: 1. We effectively combine the advantage of both hard and soft clustering, leading to a more accurate clustering result. Second, the delay association method enables the possibility of using incremental spectral clustering, which in turn lead to a large reduction in complexity and computational time. Thank you everyone for attending this session. I am disappointed that I could not attend in person, and I'm grateful for opportunity of pre-recording this presentation. If you have any question or comment, I would love to hear it from you at this email address. Enjoy the rest of your conference. Thank you.